Hello everyone, myself Dr. Seema from Alobasics. Today we'll discuss AC circuits, which is 13th chapter from Maharashtra State Board Physics syllabus. Let us discuss power in AC circuit. Earlier we have studied resistor, inductor, capacitor connected with AC. Even we have studied they are connected in series with AC. Now in all these four types of AC circuits, how much power consumption is there? That we have to discuss today in detail. So let us start with first topic on power in AC circuit, that is average power associated with resistor. Earlier we have studied a resistor connected in an AC circuit, how it behaves, and we are familiar that in that circuit EMF and current are in phase. And as EMF and current are in phase, we can write equation for this as E is equal to E0 sin omega t and I is equal to I0 sin omega t. Now, again in 11th standard, we know that we have studied power in electric circuit, which is given by P is equal to potential difference multiplied by current. Now here, potential difference is replaced by EMF in case of AC circuit. So we write down power as P is equal to E into I, and we'll substitute values of E and I in this equation and we'll solve it mathematically further. Now this instantaneous power varies with time, and due to that, while solving this, we have to consider average power over a complete cycle. The same technique we'll use which we have used for determining average power of EMF and average power of current. So here we'll write average power is equal to work done in one cycle divided by time for one cycle. That is nothing but integration for one cycle, that is 0 to t, p dt upon t. And now here we'll substitute the value of p in this circuit and we solve it, and after solving this we come to the equation that P average is equal to E0 upon root 2 into I0 upon root 2. Now we know that E0 upon root 2 is ERMS and I0 upon root 2 is IRMS. So we can write this power, average power, or the power, purposely I am writing this as a P, will come to know about it, that is equal to ERMS into IRMS, and this power P is known as apparent power. Now let us discuss on power associated with an inductor circuit, and we know that in pure inductive circuit alternating EMF leads alternating current by phase angle pi by 2. So equations we can write E is equal to E0 sin omega t. As EMF is leading means current is lagging, so here there will be minus sign, and I is given by I0 sin omega t minus pi by 2, which we can write as minus I0 cos omega t. Link of this video is given in description box. Again, we are going to use same procedure here. We are writing instantaneous power, we are substituting values for EMF and current and simplifying this over a complete cycle to get average value, and we come across that P is equal to P average, that is equal to 0. So here we can note that for inductive circuit average power over a complete cycle is 0. Now average power for the complete cycle for AC circuit consisting of pure capacitor, and for pure capacitor we know that is alternating EMF lags alternating current by angle pi by 2 radian. Now here again I'll write down equation for E is equal to E0 sin omega t, and as current is leading here, plus sign is indicating that leading of current, and we write I is equal to I0 sin omega t plus pi by 2, which we can write as I0 cos omega t. Now further procedure is again same as which we have seen for resistor and inductor, and we come across the value of P, average value of power in capacitive circuit, and that comes again 0. So we can write P is equal to P average is equal to 0, and here again we can say that the average power of capacitive circuit over complete cycle is also 0. So what we have seen, in case of resistive circuit, average power is ERMS into IRMS. For capacitive and for inductive circuit, average power is 0. We'll discuss on average power associated with LCR circuit. In LCR circuit, we know that there is EMF also, there is inductor also and capacitor also. And in general, when we have discussed this series LCR circuit, we have seen that alternating EMF may lead or may lag alternating current by phase angle phi. So we write here these equations as E is equal to E0 sin omega t. Then I is given by I is equal to I0 sin omega t plus or minus phi. Why plus or minus? If current is leading, sign will come plus. If current is lagging, sign will come minus. So we can write it as by plus or minus. See, whether you are talking in terms of EMF or in terms of current, that will decide whether it is leading or whether it is lagging. Earlier I told you how to keep in mind that with the help of civil, very easily you can keep in mind that whether it is leading or whether it is lagging. The further procedure for determining average power is same as earlier. We'll substitute values of E and I, and we solve the mathematical expression for that, and we come to the equation that power is given by E0 I0 upon 2 into cos phi. This t and this t is cancelled. So E0 I0 upon 2 we can write as E0 upon root 2 into I0 upon root 2, and due to that we can write this expression as P average is equal to ERMS into IRMS cos phi. Here I'm having additional factor of cos. I'll continue with the same equation that P average is equal to ERMS into IRMS cos phi. As I told you, here we are having additional factor of cos phi, and ERMS into IRMS is already existing for the power in resistive circuit. The average power which we are having is known as true power. It depends on RMS values, ERMS and IRMS, and the phase difference between them, that is phi. The apparent power P is given by ERMS into IRMS, which we have studied for pure resistive circuit. I can write this equation in terms of pure power, true power and apparent power also. So I can write true power is equal to apparent power into cos of phi also. The factor cos phi is known as power factor. So in this equation, what we are considering, cos phi is power factor, And earlier I told you that true power is equal to apparent power into cos phi. So I can write cos phi is equal to 2 power divided by apparent power. So what I am having? True power divided by apparent power, and same thing we can write in terms of impedances. And for that purpose, we'll consider impedance triangle which we have studied earlier. In this triangle, we can see that this on x-axis R is there. Here on y-axis I say XL minus XC is there, and the vector is represented by Z, which is under root of R square plus XL minus XC bracket square. This is a simple right angle triangle where this angle is said to be phi. Now from this diagram, I can write value of cos phi, and cos phi is equal to adjacent side divided by hypotenuse. Now what is adjacent side? Adjacent side is R and hypotenuse is Z. So we write cos phi is equal to R by Z, or that is equal to R upon under root R square plus XL minus XC square. We are writing it as an impedance triangle for XL minus XC. Earlier we have seen impedance triangle for XL is less than XC also. And in that case, instead of having this vector in upward direction, we have it in the downward direction. That is the only difference. So we can find out power factor cos phi, which is based on the equation. Either we can find out in terms of power or in terms of impedance also. If I have a non-inductive circuit, in that case XL is equal to XC, or the same circuit is said to be purely resistive circuit. We have studied resonance circuit, where we apply XL is equal to XC, the circuit becomes purely resistive circuit. And for such a purely resistive circuit, as XL is equal to XC, this quantity becomes 0. As this quantity becomes 0, we can write down cos phi is equal to R divided by R, and that is equal to 1. If cos of phi is equal to 1, what will be the value of phi? Value of phi must be equal to 0. In that case, we say that for cos of phi to be 1, or for purely resistive circuit, value of phi is 0. That is, phase difference between current and EMF is 0, or there is no phase difference between EMF and current. Now power dissipated in circuit is due to resistor only. Power dissipation किसकी वजह से है? सिर्फ रेजिस्टर की वजह से है. यहाँ पे ना ही इंडक्टेंस कोई रोल प्ले कर रहा है, नहीं कैपेसिटर कुछ रोल प्ले कर रहा है. हमने पहले भी देखा इंडक्टिव सर्किट में पावर 0 थी, कैपेसिटिव सर्किट में, प्योर कैपेसिटिव सर्किट में भी पावर 0 थी. और पावर कहाँ पे थी? तो प्योर रेजिस्टिव सर्किट में पावर थी. इन प्योर इंडक्टिव और कैपेसिटिव सर्किट phi is equal to 90 डिग्री. अब मैंने पहले ही बताया कि पावर 0 थी. पावर 0 थी, इसका मतलब क्या था? Cos of phi is equal to 0. Because ERMS is not 0, IRMS is not 0. So what is 0? Cos of phi is equal to 0. What is phi? Phi is the phase difference between EMF and current. And we know that if cos phi is equal to 0, then phi must be equal to 90. And we are knowing that in inductive circuit and capacitive circuit, always there is a phase difference of pi by 2 between EMF and current. Same thing, we are getting that there is a phase difference of 90 degrees, or there is a phase difference of pi by 2 radian, and power factor is 0. As power factor is 0, we say that no average power is consumed in inductor and capacitor. As earlier I told you, power is dissipated in resistor only. Same thing now I am writing as no average power is consumed in inductor and capacitor. When average power consumed in circuit is 0, then the current in the circuit is known as wattless current or ideal current. So this is the condition for getting ideal current, or this is the condition for getting wattless current. What is meaning of wattless? There is no power. There is no power means there is no energy. As there is no energy, we say that there is no watt energy existing, and due to that we consider it as wattless current. The average power consumed in circuit is 0, then current is wattless current. But if power is consumed in the circuit, we cannot call it as wattless current or ideal current. Actually, there is no existence of wattless current or ideal current, because we cannot say that average power consumed in circuit is 0. There must be at least little amount of power is consumed in circuit. If it is negligible, we can consider it as wattless current or ideal current. So this is all about power associated with resistor circuit, inductor circuit, capacitor circuit, and series LCR circuit. Today's topic was another important topic regarding exam point of view. And on this topic, varieties of questions can be asked. I have listed few questions here which you can solve, you can practice and prepare for your exam. Today's topic, we have seen power in AC circuit. And while studying this power in AC circuit, we have discussed about power in all sort of AC circuits which we have studied earlier. One more thing you have to keep in mind, that when I'm considering series LCR circuit or power associated with series LCR circuit, then at that time you can apply same technique for power in series LR circuit as well as power in series CR circuit also. Only the thing is that you have to consider, if you are considering LR circuit, you have to take reactance of inductor. If you are taking CR circuit, you have to consider reactance of capacitor, and you can put up those values in the equation and you can simplify this, or you can solve numericals on this very easily. Thank you for watching. See you soon in the next video of AC circuits.